Hi there, my name's Andrew Brown. Welcome to Real-Time Music and Sound with Pure Data. In this episode, we're going to be looking at wavefolding. So to get started, we'll create ourselves an oscillator. Can be at any frequency. Let's choose 172. And as with most of our patches so far in this series, we'll provide an amplifier as a volume control and a DAC as the output. Connect all of those together like so, and we'll create a value for our volume, and we'll change the properties of that so that it goes between 0 and 1. So this should give us an oscillator, which it does. You can see the sine wave here. Because our oscilloscope display is going to be particularly important for this, we'll create our one inside PD as well. I'm going to call this array display, $0 display. Make it 500 elements long, drawing with a polygon, and so there's our waveform display. In order to write to that display, we use the tab write function object and tell it which table to send to. In this case, it's the display array. We need to trigger that regularly, and we use a metronome to do that every 100 milliseconds. And we need to start our metronome, be able to start and stop it with a toggle object. We can then pass our audio data to the display, start it up, turn the volume up, and we can see that we've got that working there. All right. Now, the next stage is that what we really want to do in this case is we're looking at creating harmonics by distorting this wave using wavefolding. So we need to be able to increase the volume of the oscillator even beyond the maximum output gain. So I'm going to add another volume control in here which we can adjust independently. This volume control I'm going to use a slider to control, just to get a bit more accuracy. The properties of this slider, we're going to have a minimum volume of 1, so it's a unity, and we'll go up to a maximum of 7. Give it a color just to make it a little bit more obvious on the screen. So now we're going into here. The default value, the lowest value rather, is 1, so that should just give us exactly the same output when we start it. And there it is. If we want to see the output of that on our display, we can connect it to the tab right, and all things are going fine. Now if we turn up this gain control here, we will see that the wave is exceeding the range of our display. Our display by default goes from positive 1 down to -1, which is the normal range. The reason that it's clipping here or exceeding the range here and not over on my main oscilloscope is because of the gain control here on our standard output. But without blasting our ears out with that, we can see visually that we're exceeding the range of our display, which is our range here. Now, one thing which we could do in this case to distort the wave, which we've seen in a previous episode, is we could limit the output using the clip object, or the clip tilde object in this case for audio, and that would chop off these exceeded range sections, and we would get a sort of a cut off section at the top here that would change the timbre. What we want to do for wavefolding is, instead of chopping off these exceeding parts, we want to fold them back inside the display range. So that instead of just stopping them, if it exceeds by a certain amount, we want to draw it back inside by a certain amount, kind of like the top and the bottom of this display are acting like mirrors. So that's the basis of wavefolding. In order to do that, we are going to introduce some math to process our audio. We could do it with a sort of complicated formula set of patches, but in PD we have this wonderful object called expression tilde in this case, because we're working on audio waves, and this will allow us to put in a kind of mathematical formula or a code, bit of computer code that will deal with this folding process. What we want to say is if the waveform exceeds this maximum boundary, we want to fold it back in there. So we use an if statement to begin that process, and we say if the input, which is indicated by this variable $v1, if the input is greater than 1, because 1 is the top of our display, then what we will do is change that signal so that it's equivalent to the formula 2 minus $v1, which means it's 2 minus whatever the value is. So if it's 1.5, then it'll be 2 minus 1.5, which will bring it back down to a half. And so that's the way in which it gets folded back in. If it's not above the top, then we'll just send the signal out unchanged. Just written on. All right, so there we have our formula for doing that. So let's see how this works. We can connect it all up. I can take the output of that to the display so we visualize what's going on. So as we increase the volume, now we can turn that up so we can hear the effect as well as see the effect. As we turn up the gain, you can see and hear that we're getting a different result than before. Timbrally, we're getting a richer sound. It's introducing additional harmonics, which we can see on the spectrum analyzer. And you can see that the display, on this display and on the oscilloscope, that indeed it is folding the wave back inside. So, success. However, only partial success, because we haven't dealt with the case if the waveform exceeds the bottom. So let's deal with that now. I'm going to disconnect a bunch of these for the minute. We will use a similar, copy and paste that, because we're going to use a very similar expression for dealing with the bottom. We just need to change it so that it says if the input value is less than -1, which means it's less than what's going down here, then we need to have -2 minus the thing, so -2 is down here, minus the value will bring it back up inside. And that should help us deal with the going out of range on the bottom. So let's have a listen. So there we go, magic, and have a listen, and we can hear that that is indeed what's going on. So as we increase the amplitude, we increase the amount of folding, and you can also hear that we're increasing the amount of upper harmonics. So it's getting brighter and brighter and brighter, and you can sort of see that on the spectrum analyzer also, as well as hear it. As we keep going though, we do get this problem that it folds, the bottom one's folding over so much that it doesn't cut it back off at the top again, because that's coming out after this second formula. So the quickest way we can deal with that is simply to apply these formula a second time, so that even after it's checked the first time, if the folding is even more drastic and needs to be folded back in a second time, then we add that maths, which is exactly the same formula, but we'll cope with the situation where our amplitude's even higher. So now let's have a listen. We're at this stage, that's great. And if we keep going up, folds fold back in, we keep adding more and more higher spectra. And so you can see we've magically turned our sine wave oscillator into rich sounding waveform by folding the wave back inside as we go. So have an experiment with that, and I will see you in the next video. Thanks.